Okay, now that we had a peek at how they figure out the structures, we're going to look at the structures themselves. So the crystalline lattice is the regular arrangement of atoms in a crystalline solid. And the particles are going to take on that arrangement because it lowers their potential energy. So here we could look at this two-dimensional representation, and each of these circles would represent the center of an atom or an ion, and that's the lattice. A unit cell is the smallest piece of a crystal that if you repeat it in 3 dimensions, you'll get the whole crystal lattice. So for this example in 2 dimensions, if I take from the center of this circle over here, over here, over here, and I take that and I just copy that over and over and over again, I'm going to get this same structure. Right? There's another one. There's another one. There's another one. Okay. Does that make sense? So there are a lot of different unit cells. Ones that are called cubic unit cells are going to have equal lengths on their sides. They're going to be cubes, right? Equal edge lengths, and they're going to have 90-degree angles. There are a lot of other types of unit cells, though. Some of them have right angles but different lengths, like these two, or some of them have different kinds of angles in them. So just so we know what we're looking at, when we're looking at the next few slides, any atom in these structures is identical to the other atoms, even if we've colored them differently. The different colors are just so that we can see them better, because it's just hard to visualize this 3-dimensional stuff. A couple of terms we use: coordination number. That's how many atoms each atom is in direct contact with. It's actually touching. So that's the number of atoms that an atom can interact with strongly. And then packing efficiency is the percentage of the volume of the unit cell that's actually occupied by the spheres of the atoms. There's always going to be some empty space because you can't pack spheres together without empty space. These are related to each other. A higher coordination number means you have a higher packing efficiency. Okay, so we're going to look at 3 different cubic unit cells. This is kind of a summary of them, and we'll look at each of them individually. So the simple cubic unit cell has 1 atom at each corner of this cube. And so if we take this and we duplicate it and put it next to it, then we're going to fill in some more of this atom, right? And fill in this one. And then if we put another one of these on top, it's going to fill in. And so if you put enough of these together, you're going to have a whole atom in each corner. Here the atoms are touching along the edge of the cube. The edge length is called L, and R is the radius of the atom. So because these touch along the edge, then L is equal to 2 times the radius of the atom. If we were to take all these pieces of an atom and assemble them, we would find that we could make 1 complete atom out of them. Because at each corner, we have 1/8 of an atom. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 eighths, and so we could put all those together and make a single atom. So in this unit cell, there is the equivalent of 1 atom. So this is what we were just looking at. And here is if we filled in all of the atoms at the corners, right? And so this like gray box in here, That's the unit cell. Here we're looking at these spread out a little bit so that we can see, well, how many atoms is this guy in the middle going to touch? Well, he's going to touch one on the right and one on the left and one on the top and one on the bottom and one in the front and one in the back. So any of these atoms is actually touching 6 other atoms. That's the coordination number. The packing efficiency of this is 52%, which means it's almost half empty space. Any questions yet? Other than maybe, what the heck? It's not actually a question, though, is it? So here they're asking us to calculate the packing efficiency of a 2-dimensional lattice, just because this is easier to do than 3 dimensions. So this is like a 2-dimensional version of that simple cubic unit cell, where we have the center of an atom at each corner of a unit cell. So the packing efficiency is how much, in this case, of the area would be the area occupied by atoms divided by the total area times 100. That's going to be the packing efficiency. So if we look at this unit cell here, how many atoms are in, or circles are in that square? There's a fourth of a circle over here, and a fourth of a circle over there, and a fourth, right? So that's a total of 1 circle, right? In that is the equivalent of 1 circle. So we have 1 circle. The area of a circle is pi r squared. So we've got pi r squared, and then we need the area of the whole square here. So I'm going to draw that down here because it's not big enough. So we've got these circles, right? And they're touching on the edges. Well, that one didn't touch. They're touching on the edge. That's not a circle. These are harder to draw. Yeah, I give up. But here's a radius and here's a radius, right? So the edge length of this, L, is equal to 2 times the radius. So my square here is 2r on each side. What is the area of the square? It's the length times the width, right? So I don't know why I wrote pi there. I was thinking about Thanksgiving, maybe 2r. So the area is 2r times 2r, right? Which we could also call 4r squared. So the total area is 4r squared, and then we're going to multiply that by 100. We don't know what the actual radius is. Turns out it doesn't matter because the r squareds cancel out. And so we end up with pi over 4 times 100. So pi divided by 4 times 100. And my calculator so thoughtfully tells me 25 pi. Yeah, that's not so helpful. Okay, 25 times pi. There are a series of buttons you can push to get it to finish that for you. 78.5%. Any questions? The second cell we're going to look at is called the body-centered cubic unit cell. And here we have one atom that's in the middle of the unit cell. It's in the body, right? So this gold-colored atom is the same kind of atom as the purple ones. We just made it a different color so that we could see it better. Otherwise, it ends up looking like a blob of purple. So there's one atom in the middle, and then we still have an atom centered at each corner. So this one, those purple ones, we know from the previous unit cell, those add up to one atom, plus this atom in the middle. So in this unit cell, there are two atoms. If we want to calculate the edge length in terms of R, this becomes a lot more complicated because the atoms don't touch along the side, they touch diagonally through. And so there's the geometric proof of how we end up with L is 4R over the square root of 3. So the number of atoms per unit cell, we've got an eighth at each of the 8 corners, plus the one in the middle, so 2 atoms. Being able to identify how many atoms are in the unit cell is way more important than being able to do any calculations with the edge length stuff. This is what it looks like using whole atoms, and here is where we can see what the coordination number is. Well, in theory, we can see what the coordination number is. I know what I'm looking at, and I still find that actually pretty confusing. They're trying to show us that this one in the middle is going to be touching 8 other atoms. And so the packing efficiency here is 68%, which is a little higher than the simple, where the atoms were touching 6. So there's less empty space. An atom has a radius of 138 picometers and crystallizes in the body-centered cubic unit cell. What is the volume of the unit cell in cubic centimeters? So we're going to run across questions like this in the homework. There might be one on an exam. I will give you information like the equation for the edge length. I don't expect you to remember that, okay? So this one, we're doing a body-centered cubic. So before I forget, the edge length is equal to, I forgot already, 4R over the square root of 3. 4R over the square root of 3. So we have our unit cell, it's L on each side, and this is telling us that the atom has a radius of 138 picometers. So R then is 138 picometers. This is asking us, what's the volume of the cell in cubic centimeters? Well, how do we find the volume of a cube? Length times width times height. And for a cube, they're all the same, right? So the volume of this cube is equal to L cubed, which is the same as 4 over the square root of 3 to the 3rd power. It wants the answers in cubic centimeters. Here we've got picometers. If we just use this number, we're going to end up with cubic picometers, which is not necessarily a bad thing, but then we're going to have to convert that. And converting units raised to a power tends to mess with students' minds. So let's avoid doing that. Let's convert this to centimeters before we cube it, okay? So one way we can do that, we can convert this to meters very quickly by probably looking up what pico means. It's 10 to the minus something. It's smaller than nano. Nano's minus 9, so this is minus 12. meters. So except for deci and centi, all of those powers are factors of 3. Or multiples of 3, I should say. Okay, so now we've got meters. Let's convert this to centimeters. I'm going to multiply by centimeters, divide by meters. Well, 1 centimeter, centi stands for 10 to the minus 2. So in my calculator, I'm going to say 138 EE minus 12 divided by 1 EE minus 2. And then my calculator shows me this. Yeah. What's weird about that? This is 138. How did it become 14? Why did the calculator round that? Because if your calculator is set to display decimal notation, it will do that if it can. And it'll do it even if it has to round to 1 non-zero digit. So if I tell my calculator to show me this in scientific notation, it's going to show me 1.38 times 10 to the minus 8. And that will be our centimeters. So just watch out for that. Well, I used up an awful lot of space there. I'll stick that down there. And maybe change colors. So my volume is going to be 4 times the radius in centimeters divided by the square root of 3, and that whole thing raised to the 3rd power. So how you enter that into your calculator is going to depend on what kind of a calculator you have. That's what I got. Is that a reasonable number? It should be really, really small, right? Because this cubic unit cell has the equivalent of 2 atoms of whatever element this is, right? 2 atoms. It should be way too small to see. So 10 to the minus 23rd cubic centimeters. Let's see if I did that right. Oh, I didn't. Oh, cool, I did. Face-centered cubic unit cell. So again, a cubic unit cell, we've got equal lengths on the edges, and we have right angles. But here, instead of 1 atom in the center in the body, now we have atoms that are centered on the faces of this cube. So we have half of an atom here, and half centered up there, and half down here, half on all of those. And we still have the ones in the corners. So now this one touches just on the diagonal of one face, and this is the math involved in finding out that the length of the edge is going to be 2 times the square root of 2 times r. So this does not mean 2 times the square root of 2r. That's not what it is. It's it would probably be better to say R times 2 times the square root of 2. So counting up the atoms here, we've got a total of 1 from all the corners. Each face is half of an atom. There are 6 faces, so that gives us 3 more atoms. So this has a total of 4 atoms in it. The packing efficiency here, I mean, they didn't even bother drawing those dotted lines this time. I don't know how you're supposed to make any sense out of that. But the coordination number is 12. Oh, good. Like we needed to know that. The packing efficiency is also higher, 74%. Here's another one of those body-centered cubic unit cell calculations. Here they're telling us this is chromium. And the radius of the chromium atom is 125 picometers. Calculate the density of solid crystalline chromium in grams per cubic centimeters. So they gave us just one number, and they're asking us to calculate the density of this stuff. Well, here, calculating a density, we can use the density equation. What's density? Mass divided by volume, right? Mass divided by volume. So if we could calculate the volume of a unit cell, which we've already done, right? Then that would be the volume here. Now what we need is the mass of one unit cell. So the mass of one unit cell divided by the volume of one unit cell. So the volume is going to be, see if I remember, 4r over the square root of 3 cubed. It's not a very good 3. Here, because we want cubic centimeters, we want to convert this into centimeters instead of leaving it as picometers. 125 picometers is 125 times 10 to the minus 12 meters. And then converting to centimeters. We're doing tally marks for the train because it's just less disruptive. Yeah, so this is going to come out to be 1.25 times 10 to the minus 8 centimeters, right? So we can plug that in here. 4 times 1.25 times 10 to the minus 8 centimeters divided by the square root of 3, whole thing raised to the power of 3. .4056 times 10 to the minus 23rd cubic centimeters. That's, same ballpark as that other one, right? So that's the volume of the unit cell. It's teeny, teeny, tiny. How do we find the mass of the unit cell? We're going to use the molar mass to calculate that. So how many atoms are in one unit cell? This is the body centered. So the corners make up one atom, and the atom in the center makes a second atom. So there's 2 atoms total in this unit cell. 2, yeah. So 2 atoms per unit cell. Well, we've got a molar mass from the periodic table that's in grams per mole. How many moles of atoms is 2 atoms? Well, 1 mole is Avogadro's number of atoms. Yeah.
How did you know that there's 2 atoms in this specifically? Like, what gave it away, or how did you just know that?
Because it's body-centered cubic. So it's this one.
Okay.
Okay. So body-centered cubic. So we were canceling, we had 1 unit cell, there's 2 atoms in a unit cell, there's this many moles in there, and then we want to get to grams. So chromium, periodic table says 51.9961. 51.9961. So the mass, 1.72687 times 10 to the minus 22 grams. So we'll take that really tiny number and divide by the really tiny volume that we got. And we're going to get 7.18 grams per cubic centimeter. Is that a reasonable density for a metal? Metals are more dense than water, right? Water is 1 gram per cubic centimeter. So, yeah, that's reasonable. Any questions? Get through to where we were. There we go. So this kind of a question is a more reasonable exam question. How many atoms are in the unit cell in the face-centered cubic structure? So what you want to be able to do is, in your head, think about, well, what does that mean? Face-centered. All of these unit cells have atoms at the corners, right? So there's 1 atom if you take all the corner pieces. But the face-centered, you also have an atom centered on each face. So that's half of an atom. So we have 6 sides times 1/2 of an atom on each side. So that's going to give us 3 atoms plus the corner atom. So 4. And questions along this line do often show up on the ACS final exam. They'll give you like a picture and ask you what kind of a unit cell it is, or they'll ask you how many atoms or ions are in the unit cell. So another way we can look at crystal structures is to think about stacking these atoms together in layers. This is the simple cubic, where we just have atoms at the corners. And this is making a grid, basically, of atoms, and then stacking another layer on top. So each atom is directly above the atom below. There's a lot of empty space here. if you try to do this with marbles or billiard balls or oranges or anything round, you'll find out it's actually kind of hard to do this, right? Because this atom doesn't want to sit on top of that one. It wants to fall into the little divot between 3 below. A more efficient packing is achieved by, instead of having, well, let's see here. So that other one, you've got these lined up like this, right? One row directly next to each other. Here, we have this row is offset from that row. And so they can snug in a little closer to each other. You see that? So we offset one row by half an atom, and then they can pack in more closely together. And then we're going to think about, well, how do we stack these layers on top of each other? If we take that second layer and move this over a bit, so it's offset, so that this, this guy right here. So this guy is sitting in this little divot here made by those 3 atoms. And so this is what things more like to do, oranges, marbles, etc. They're going to get as close as they can because gravity's pulling them down. So we've got layer A, and then we have layer B. Both of those are called closest packed because you can't get any closer. They have the same packing efficiency, 74%. They have the same coordination number. But how you put the third layer on is different. So what's called hexagonal closest packed, you've got layer A, layer B, and then layer A is directly in line with the first layer. The third layer exactly lines up. So that's called an AB-AB pattern, and that gives you a hexagonal unit cell, which is one of those that we showed at the beginning and didn't really talk about. Come on, advance. There we go. So if you take your layers A, B, A, so the blue one here is directly above the blue one down there, this would be the unit cell, and it's hexagonal. Okay? That's why it's called hexagonal. And then we have another type of closest packing where the third layer is offset from the first layer. So here, this layer is not in line with either of the other 2 layers. And this actually gives us a structure that's identical to the face-centered cubic unit cell. So here's our 3 layers. There's the first layer. The second layer is offset from the first layer. The third layer is offset from both of those layers. And then the fourth layer now is going to be in line with the first layer. So imagine pushing all those together, tipping it on its side, and chopping it, and you get that, which is the face-centered unit cell.